What's up, everybody? Okay, let's get it going. This is going to be the last lesson in this course. It was a very challenging course, of course, but so far we did good, and let's try to make the most out of our semester by just talking a little bit of what is this. Now, this is still within the realm of inferential statistics. So, on inferential statistics, we talked about the different types of t-tests that exist. So let's remember, the one sample t-test is used to compare one group of people with the population, a sample to a population. That's the one sample t-test. You have then that independent samples t-test. This is taken to different groups of people and you're comparing something among them. If you have a related samples t-test, you take the same group of people and you test them twice. I believe I made an emphasis on this, but I want to re-say it one more time. When you make your comparison, it can be two different groups of people or the same group of people being tested twice. It's very obvious sometimes when you see two different averages, two different means. So a person that is not well versed on statistics may right away come up with a conclusion and say they're obviously different. If I want to compare my grades of the students in my social psychology class with my students in my abnormal psychology class, and in one class they get an 85 and the other one they get an 80, I may be super tempted to say they're different, it's obvious, look at the differences. But here's where we have to be careful, because the groups means being different is not telling the whole story. Maybe the groups have different numbers of people, maybe the groups have different variability. If you take the standard deviation of each mean, perhaps the standard deviation of one may be huge because you have an extreme score, also called an outlier, that is messing the results. So a t-test tries to be a more fair comparison by not only taking the means, but also taking into account the variability that both have to see if statistically there is a difference. The ANOVA would be the last thing that I would have taught you if we had a face-to-face class in the semester. But it's very challenging to teach this from an online perspective. So what I want, and I'd be super happy, is that at least, not if you know how to compute it, but at least you know what it means. So pay attention because I'm going to explain what it means. ANOVA is an acronym for analysis of variance. Analysis of variance. So the analysis of variance is trying to analyze how much variability exists, but what is the difference between this and the t-test? Pay a lot of attention. The analysis of variance tries to compare more than two groups. A t-test compares two samples. Could be the sample to a population, can be the same sample being tested twice, or can be two different samples. But what happens when you have three samples? What happens if not only do I want to compare the differences among my social psych and my abnormal psych students, but I also want to bring in the introduction to psychology students? I have three different samples, then I do the ANOVA. So the ANOVA can be a little bit longer to compute, but it's a more fair way to measure all 3 or 4 or 5 or 6 different samples. It doesn't matter how many you want to. When it's more than 2, then you don't no longer do a t-test, you do an ANOVA. And there's often a common question, why couldn't you just make multiple t-tests? Say if you have 3 samples, why can't I just do different t-tests to compare all 3 groups? Remember alpha. Alpha is the probability of making an error. So the thing is, when you make multiple t-tests comparing the same 3 samples, typically alpha goes all the way up. What is the probability, what is the level of alpha that you need to be published? Think about it. 0.05 at least. If you want to get published, you want at least at 0.05. When you have multiple t-tests, that goes up, goes up, goes up, goes up. So there's no journal that will accept your study. You're not doing anything really. The ANOVA compares the 3 samples while holding the alpha level low. Make sure you make a note about that. This compares more than 2 groups while keeping alpha at 0.05 or less if you were to want that. So that's the purpose of ANOVA, all right? That's the purpose of the ANOVA, compares more than 2 samples while keeping the alpha level low. Now, the goal. The goal of an ANOVA, and if you want to, you can see it on the slide so you at least have an idea, but the goal of the ANOVA is to, same with the t-test, compare a critical number to an obtained score. The difference is in the ANOVA, you use a different set of numbers, also called the F-test. The F-test. And the F-table, my bad. The F-table. The ANOVA is also called the F-test because it's based on the F-table. And the F distribution, based on degrees of freedom, is gonna be able to show you how to find the critical value. And then you're gonna run your ANOVA and you're gonna compare it to your F obtained value. If your F obtained value is higher than your critical number, then, you guessed it, you reject the null hypothesis. If it's lower, then you fail to reject the null hypothesis. So the goal is for your F obtained value to beat the F critical value. Alright? So far so good. Cool? Now, this is where it gets a little bit more complicated, so pay attention. If you have your F obtained value being higher and you reject your null hypothesis, if you have 3 groups, say in my case I'm trying to compare abnormal with social with intro, and my F obtained score is higher than the F critical, what would be my conclusion? My conclusion would be that there's a difference among the means of those 3 groups. That's the goal of the ANOVA, saying statistically those 3 means are different. But this is not enough to tell us where the difference is at. So in the ANOVA, you take on a different thing called a Posthoc. This is sort of like the measure of effect size. We do this only when you reject the null hypothesis. So what you do with a Posthoc is you reject the null hypothesis, and the thing that follows is a measure that will try to compare the means to see which means are actually different. The post-hoc comparison, there's different ones, but for example, say the most common of all is called Tukey's cube. So what you do with Tukey, you're going to find that critical score on a different table called the Tukey table, and in that table you're going to find a critical value, which is going to tell you, say, to give up a number like a 3. You're going to make comparison among the means, and the numbers that are higher than that critical value, those means are different. It's like doing small t-tests after you rejected the null hypothesis. So, if for example, my critical value is a Q of a 3, and I compare the scores from my abnormal psychology class to my social psychology class, and the difference in those means is a 5, then I can say statistically those 2 means are different. And then I compare my abnormal psychology class to my intro to psych class, and the difference in those 2 means is a 2. Because my critical score is a 3 and over here is a 2, those are not statistically different. You may need to rewind on that. But in essence, Posthoc gives you a critical value, and you're going to compare the means, and if the number of the means is higher than this, then it means that those means are significantly different. See why it's hard to, it sounds hard, but looking at the slides, it's a little bit easier to understand. Now, the last thing, and let's wrap it up. The last thing here is ANOVA can be between subjects or can be within subjects. Between subjects implies that you have samples made of 3 different groups of people. So the idea would be that my students in my abnormal, in my social, in my intro classes are not the same. Those are all different people. That's a between subjects design. And a within subjects design is the same group of people being tested 3 times. So the students that are in my ANOVA, in my intro psych class, in my abnormal class, and in my social psych class are the same students. That's a within subjects design. Last thing, if I only have one independent variable in mind, if I want to see overall the level of difficulty in the class based on the subject, so my only interest is how the subjects are going to affect grades, that's one independent variable. That's called a one-way ANOVA. But in the ANOVA, you can incorporate multiple independent variables. So say that not only am I interested in how the students are going to change their grades based on the subject that I'm teaching, but also I want to see how the students are going to be affected by the class going online in the middle of the semester. I bring in 2 independent variables, so now that's called a 2-way ANOVA. And there can be a 3-way ANOVA. You know what? It's not only that I'm interested in the difficulty of the subject, not only on the classes going online, but also I want to see what is the effect of the stress of being in quarantine in the middle of the semester. So I have 3 factors now. That's a 3-way ANOVA. And ANOVAs can get crazy because you can have a 5-way ANOVA, 6-way ANOVA, and the computations get huge. You would see a bigger 4-way ANOVA, 5-way ANOVA, most likely in a professional setting. If you decide to become a psychometrician, and you decide to be a person that works all the way from a professional standpoint in statistics, then you're going to see 4-way, 5-way ANOVAs and so on. But if in your advanced statistics class that you should take if you want to go to grad school, in your advanced statistics class, you may start to see a 2-way ANOVA. By the time that you get it, hopefully everybody watching this is going to make it to grad school. In grad school now, you may see a 3-way ANOVA. In the professional setting is where you get to see those bigger numbers and they get kind of crazy. They can get kind of crazy. But overall, as long as by the end of this class you at least know what is the purpose of the ANOVA, I'm more than happy about it. Good work, well done.